stuff in 16 weeks, which, is it 16 weeks? Yeah, 16 weeks, which only equates to about, when you put the tests in there and stuff, it's only about 28 classes, you know, and we're trying to do that most time in high school. You got the whole year and you're in there, every day, and it's a different animal. So I tried in the beginning to kind of make your schedules, remember that? Yeah. Like, where's your time going to come from? It's because you need so much time, and it doesn't slow down. We're just going to keep going here. And then that's in the Cal 2, that's what makes that course so hard. Is it comes fast, it's difficult, it's new concepts, it's concepts that take a lot of repetition to get. Yeah, I won't get into it, but.
So do we still get into related rates and stuff like that?
Cal 2, no. Basically what we're doing in Cal 2 is everything we're doing in Cal 1 backwards. If I could sum it up. It's the antiderivative, not the derivative, the antiderivative. And the problem with the antiderivative, the biggest problem, is that you've seen how when you take the derivative of something pretty simple, it can become very ugly. Well, if you have to undo that, it's very difficult to go backwards. You have to undo chain rule, you have to undo product rule and quotient rule, which you can imagine would be difficult. And the students who are good at undoing it are the ones that are excellent at differentiation. And that's why that's the Achilles heel. If you can't differentiate, you're never going to integrate.
Oh.
You see what I'm saying? Like, if you don't see product rules in your head backwards, if you can't see that, then it's going to be difficult for you. So I'm not saying that Cal 2 is impossible. Look, there are a lot of students that get through Cal 2, but you have to be ready for it. It's not just something you just throw a student into and be like, yeah, fine, you'll be fine. Okay, let's get moving. I've eaten up 25, that's not bad. So today, let's get back on track. Let's make sure you keep up with the videos. I'm not going to give you any quizzes today. We're going to talk about exponential and logarithmic functions, which we have conveniently avoided with everything we've studied, all the derivatives. We've done trig functions, we've done polynomials, rational functions, all types of different functions, root functions, but we have conveniently avoided exponential and log functions. So let's do a little quick recap. I'm not going to do 3.1 or 3.2 out of the book, because those are reviews of exponential and log functions. It's college algebra material. But there are a few things I do want to point out just to make sure you remember. All exponential functions can be written like this, where a is a number. And we call these exponential functions because the variable x lives in the exponent, as opposed to a power function, like we'll say this versus a power function would be something like this, x to the n. So here n is a power, right? X is your variable. Here it's flipped over. This right here we call the base, and this is the exponent. This exponent is the variable. Any function that looks like this is an exponential function. And we have some restrictions on a here. A has to be bigger than 0, and a cannot be 1. And the reason we don't use 1 is because 1 to any power is 1. And that would be a very boring function. It would just be flat the whole time. The reason we don't let a be negative is because when you take negative numbers and raise them to different powers, they start flipping in signs. Like -2 squared is going to be +4, but -2 cubed is -8. So what happens is if you try and go to negative numbers for this base, you start getting what we refer to as like a salt and pepper function. It starts just jumping back and forth between positive and negative numbers, and it's not continuous. You can't draw it without picking up your pencil. So we just throw it out. We say don't consider any negative numbers, just positive numbers and not 1. This is the graph of an exponential function. In college algebra, we talked about exponential growth, right? This graph would go up and keep going up forever. And then as you come to the left, it actually has an asymptote. It flattens out, gets closer and closer to the x-axis without actually getting there. So that's what these limits mean. As x goes to infinity, the function grows without bound. As x goes to negative infinity, the function approaches 0. All right? Now, that's what it does if a is between, if a is bigger than 1. we have exponential growth if this number is bigger than 1. But if that number is less than 1, still greater than 0, but less than 1, anyone remember what happens to the graph? Starts off big and then gets small. So it just flips it over. It's a reflection over the y-axis. Just take that red one, flip it over the y-axis, you get the blue one. So that's what happens if A is smaller than 1. So like if you had like 1/2 raised to the x, it would look like this blue one. We call that exponential decay. This kind of look familiar? Yep. You know, it's been a while, but all right. Now there are also some other things with exponentials that we need to recall, and these are actually properties that we use in college algebra. We've used a lot of these properties already, so I'm just going to remind you of these. If you have, you know, something to a power times something to a power, same base, you add the exponents. These are what we call exponent properties. If you have something to a power over something to a power, same base, you subtract the powers. Haven't we done that? Didn't we have to do that when we were doing like simplifying expressions and using power rule? All right, if you have something to a power, then to a power again, you multiply the powers. And then this last one, if you have multiplication in parentheses, and you raise that to a power, as long as this is multiplication, then you can apply the power to each one. All right, so we just want to keep in mind that those properties are all on the table, right? We can use these whenever we need them. And then after we spend a couple of weeks in college algebra on exponential functions, we learn about their inverses. And we learn that every exponential function has an inverse function which undoes it. And those functions are called logarithms. So logarithms look like that when you graph them. And there's some important characteristics of logarithms that I need to point out. First, the way you write them. A logarithm is written log base a of x. So this is called the base of the logarithm. And then x is the input, that's the argument of the log function. And there are some domain restrictions. See, exponentials, they went to the left forever and to the, to the left forever and to the right forever, right? There were no domain restrictions. But with logs, there's certain numbers we are not allowed to plug in. And you can tell from the graph, if that's the y-axis, then the x that we plug in must always be greater than 0. So when we look at a log function, this in here must be bigger than 0 always, or else it's undefined. So our basic log function looks like this red one. This is a vertical asymptote. So it asymptotically approaches the y-axis. That's why I say here the limit as x goes to 0 from the right. See, we're approaching 0 from the right. Here's 0. We're approaching it from the right, and where's the function headed? Negative infinity. As the function goes out to the left, I keep on getting my left and right confused. If I go out to the right, to infinity, the function is growing slowly, right? It's not the same type of growth as exponential, but it is growing without bound. Does that make sense when I say growing without bound? Okay, just keeps growing forever? All right. Now this red one is what happens if a is bigger than 1. The blue one is if you have a fraction in there, if a is between 0 and 1. All right, that's what they look like. There's some domain issues we have to concern ourselves with. And then we have properties. And these properties are going to be very important. We will need these properties today, quite a bit. The first property, do you remember in college algebra where when you were studying logs, that you were asked to expand and condense log expressions? Yeah. Expanding and condensing. That means you have maybe you would have 4 logs together, and you would be asked to turn them all into one log. Or you have one log and they would ask you to rip it apart into 5 different logs. That technique required that you understood these three properties. The first one says, if you ever have a log, doesn't matter what the base is, and you have multiplication of two factors inside the log, you're allowed to split this into two separate logs with addition between them. Does that look familiar? Also, I'm not talking about derivatives at all right now, am I? Not at all. Not at all. These are just properties of logs. If you have a single log and you have division inside, you're allowed to split this into two logs with subtraction between the two logs. And then this one, this is really important. It says if you have the log of something, and that something, the x here, is being raised to a power, in this case r, that you can take that power and you can pull it out in front of the log and it becomes like a constant in front of the log. I'll give you an example. If you have log base 3 of x to the 4th power, I could rewrite that as 4 log base 3 of x. Okay, so that power can come out. We will use that property quite a bit. All right. Questions? All right. Now, there are a couple of very special exponential and log functions. Remember, if an exponential function looks like this and a log function looks like this, that a can be any number as long as it's bigger than 0 and not 1. There were some special numbers that turn these into very special functions. And they were called the natural exponential and the natural log function. You heard the natural log, right? So what makes this the natural exponential function is if we use the number e as our base. Now e is just a number. It's just like the number pi is a number, right? Everyone's happy with the idea that pi is a number? Okay, e is just like pi. It's just a very special number, and we give it a letter to represent it. I mean, pi is approximately 3.14 something, right? Keeps going forever. E is a number, it's approximately 2.718, and then it keeps on going forever, and it keeps changing. There's no pattern to it. These are examples of irrational numbers. So if we pick this base to be that particular number e, this is called the natural exponential function. And if we replace this a with e, that's a very special log function. It's called the natural log function. And we actually change our notation when we use this function. We don't write it that way, right? We write it with what? ln x. And I like to tell my classes a quick story about why we do that. It's because this function appears so many times, like in research, in papers, dissertations people are writing, in journals, they'll have to use the natural log function so many times, hundreds of times. I'm talking about technical journals, like technical physics journals, chemistry journals. They'll have to maybe write that 400 or 500, 600 times in their journal. And back in the days of typewriters, has anyone ever used a typewriter? No, you have? Do you know what it takes to subscript on a typewriter? So when you type on a typewriter, it's physically like going up with a metal arm with a letter that hits the paper and leaves a printed mark of the letters on the paper, right? I can't believe I'm having to explain this, but that's what it is.
Well, I mean, yeah, I've used it.
I mean, you know what they are, yeah. So it's physically doing that. So if you want to subscript, I didn't mean that bad, like personally. I'm just saying like how times have changed, right?
No, yeah.
It's just like, okay. So
PC, we're cool.
so if you want to subscript, you have to turn the drum like a little notch, and then you do E, and then you turn the drum back, and then you continue typing. Well, if you do that like 500 times, it's a pain in the ass.
You might get it wrong too.
So, and if you mess it up, then you have to take the paper out and do a little whiteout, whatever, or start over. So this is easier to type. ln x, you don't have to do any subscripting, so just a nice even flow as you're typing. And even if you're doing it by hand, it's easier to just keep writing. So it was just a convention that we used because it made it easier. But the problem with this is that people lose sight of the fact that it really is just this. It's the base E log function. That's what it is. All right. So I'll ask you all this. Here's this Excel document. What does that mean? Oh, I just did it. What does that mean right there? Save. It's a floppy disk, right?
Yeah.
And how many of you use floppy disks? Yes? You've used them, right?
Oh, yeah.
But I mean, give it another, like, what, 20 years? Like, at some point, some generation is not going to know what the hell that is, right?
Had like 2 megs if that.
Oh, yeah, man. I just think that icon's obsolete, don't you? Don't you think that icon is obsolete?
No. What else could we?
I know, right? What do you replace it with?
A hard drive?
But people don't know what it is. A lot of the younger generation doesn't know what that icon means. All right, well, here are some things that we need to know about this very special function, e to the x, and its inverse, natural log x. And that is that when you put these two functions together, because they are inverses, they undo each other. So if I take the natural log function, and inside of it, I put e to the x, what happens is that the x just pops out. I'll write it a different way, that first property. If I wrote log base e, that's the natural log function, right? Yes? And inside of it, I put e to the x. What happens is that the x just pops out. Now, why does that do that? Let me try and draw a picture. Here's where x starts, right? If you send x over here through a function and then send it back with its inverse, so if this is a function and this is its inverse, doesn't it undo it? Like x goes through, gets turned into something, then this function, which is this one's inverse, takes it right back to where it came from. So if I put x into the e function and then take the log base e of that, it undoes the e to the x and it spits back the x. Yes?
That's not just for e though, right? That's for any variable.
That would work.
Like log base e.
That would work for log base 5 of 5 to the x. That would spit out x. They have to have the same base. What we're looking at is specifically the natural log and its inverse. So if I do this one right here, that's really me doing e raised to the log base e of x. So look at that. This right here is natural log of x. So I'm taking x, I'm plugging it into the log function, and then I'm undoing it with the e function. And so it takes it back to where it was. So this just spits out the x. We also need to know that e to the 0 is 1. I hope that that's okay with you. Natural log is 1. Oh, sorry, natural log of 1 is 0. Please remember that. Natural log of 1 is 0. You can actually tell from the graph. Here's the natural log. This is any log, right? Any log looks like this. All logarithms, if you plug 1 into any log, it spits out 0. They all have an x-intercept there at 1. And then natural log of e is 1. That's another important one. Why is natural log of e 1? That's the same as log base e of what? E to the 1, right? I could say that. And so this is like the x I'm plugging in. And so this goes into e, it undoes it, and just spits that 1 out. So that's the property, that's actually the first property, isn't it, up there? It's that first property, if I replace x with 1, that's this right here. All right, we good? 11:45. All right, change of base formula, we don't need to talk about that. All right. So let me try and motivate this with an idea here. If I come in here right now and I say, what is the derivative of this? And when I say that, I mean the derivative with respect to x, all right? Everyone would say cosine x, and you'd be happy with that, I hope. But if I said, what's the derivative of sine of x squared, then what would you say? Derivative of this. So you do cosine of x squared and then times 2x. Good, that's what it would be. So that's chain rule, right? Now on the first one, did you use chain rule? Not really, but you could also say you did. Because if you look at it like you looked at this one, then you did first the derivative of the outside, which was cosine of x, right? And then you said times, good, times derivative of what's in here, but derivative of x was 1. So here we're using chain rule kind of implied, it's there. Here we have to actually write out what that piece is because it's not 1, right? When we take derivative of the inside, it's not 1, it's 2x. So we try and come up with a general formula for this. If we say sine of u, and we take the derivative, then we're going to write cosine of u times the derivative of u. Do you understand that notation? It's going to be, all right, take derivative of sine of something is cosine of that something. Chain rule says times, now the derivative of what's in here. Whatever that is, I don't know what it is. Understand? Another way I could write that is sine of a box, right? What's the derivative of sine of a box? Cosine of the box times the derivative of whatever's in that box. It doesn't matter what I use here, right? But we like to use the letter u to be like that box. That make sense? All right. With that in mind, I'm going to now tell you what the derivative of an exponential function is. I'm not going to prove it. It's a little bit tedious to prove. All right? So I'm just going to provide you with the formula. If you really want to know, that's something we'd have to sit down in my office for a while and talk about. Well, it's no, it's just I would eat up 20 minutes, 25 minutes of class, and I don't want to eat up 25 minutes of class. So I have to pick and choose my battles here. So if we have a to the x, and I want to take its derivative, so that's an exponential function, right? The derivative of it is itself, exactly, times the natural log of a. And that's the formula. Below this, I'm going to give you an example. The derivative of 4 to the x, is that an exponential function? Yes. The derivative of that is itself times what? Natural log of 4. Now, the natural log of 4 is a number. You can get on your calculator right now and you could figure out what natural log of 4 was, right? This is just a number in front of this function. I could write it this way. Natural log of 4 times 4 to the x. So look at this number out in front as scaling this function. Like if I had the function x squared, how would 2x squared look compared to that? If that's x squared, it would look like a u, right? What would 2x squared look like? A u, not move it up, it would actually stretch it out and make it narrow. This was, again, in college algebra. When you have a number in front of a function, that number either expands, like dilates it, or contracts the function. All I want you to remember is that if I have a constant in front of a function, it changes the shape of this, doesn't it? It changes it, that's all. Whatever 4 to the x looked like before, this is going to be some variation of it, stretched out or expanded out. Understand? We good? All right. So I'm not proving to you why this formula is the way it is. Let's do another one. How about pi to the x? Is that an exponential function? Yes. The base of that exponential function is pi. So the answer is going to be pi to the x times natural log of pi. That's it. We'll do a couple more. How about this? How about 4 raised to the x squared plus x? Take the derivative of this. So what do you see here? So you see chain rule, right? Yes? Maybe you weren't there yet, but do you see that you have a polynomial function that's inside of an exponential function? Instead of it just being x, right? It's actually something a little more complicated. So you step back and you say, all right, what's the derivative of 4 raised to something? Itself, right? Itself. So I write down itself. Right, that's the derivative of an exponential function is itself times natural log of, careful, natural log of 4, because that's the base, right? Just like we did here. 4 to the x natural log 4. That took care of the derivative of this. But now because of chain rule, you have to go take the derivative of what was up there. What's up there? The derivative is 2x plus 1, and I have to have that in parentheses. Now I'm going to give you a more general rule here in a second, but I just wanted to see if y'all could follow me on that. If I were to try and come up with a more general formula that I could write underneath this, that would account for the chain rule, I could write this. A to the u, the derivative of this would be a to the u, natural log a, but then one other thing, times what? The derivative of u. So that's when I put the sign up there earlier, this is what I was trying to get y'all to see. You know how I wrote that a second ago? I wrote sine u, the derivative is cosine u times u prime. Same thing I was trying to do here. So here, what was u for us here? X squared plus x. So derivative of 4 to the u is 4 to the u times natural log 4 times the derivative of u, which was 2x plus 1.
And it's always natural log, you said, right?
Always natural log of whatever the base is. Okay? Let's do another one. How about, this time I'll write y equals x squared 3 to the sine x. Pardon me? That is times. Now I'm not putting the dot there because the book is going to give you something like that and they don't put a dot there. So you need to know that that is implied multiplication here. And then I heard product rule. Correct. Everybody see the product rule? It's happening right there between these two factors. So if I want to find y prime, I'm going to do the derivative of the first one times the second one plus the derivative of the second one times the first one, right? What's the derivative of the first one? 2x times 3 to the sine x. Well, no, hold on. We're still in the product rule. That was the derivative of this times this plus, now what's derivative of 3 to the sine x?
That one's going to be 3 to the sine x
Itself, 3 to the sine x times natural log 3 times cosine x. Almost done. Times x squared, because we have to finish off the product rule, right? Yeah, there's a lot that we have to keep track of, right?
Well, would the x, well, wouldn't these be in parentheses?
Which ones?
The 3 sine x times the natural log 3.
If there was additions between these, we would need them in parentheses, but they're not. So multiplication doesn't matter. Any questions?
And that would be the final.
We could look at that as a final answer, but I also notice I've got some common factors in both of these. So I'm gonna factor these. And in the homework solution videos that are up online right now for you, I've started to do more simplification of my answers because, again, of where we're going. So I'm going to now write, let's see, I notice they both have an x, right? This has x squared, so I'll pull one factor of x out. I also notice I have 3 sine to the x appears in both factors, right? I have a 3 to the sine x here, a 3 to the sine x here, so I can factor that out. What would be left inside this parentheses if I pulled x 3 to the sine x out? Out of this factor, or this term, I would just have a 2. Plus, and then here, this has been pulled out in one of the x's, so I'm still going to have ln 3 cosine x and another x. And you can write that however you want. I'm going to write it this way. This is all multiplication, so it wouldn't matter what order those are in. I have the x that was still here. I have the natural log 3, which is still here, and the cosine x, which is still here.
You just sort of write that like x cosine x.
Yes.
Natural log 3, right?
Yep.
That's cool.
You could do that. All right.
That 3 sine x out there is going to mess up the... Oh, wait, never mind. It's all connected.
No.
Never mind. It's like
You're good.
X, whatever.
All right, so that is the derivative of an exponential function. Now, what is the derivative of e to the x then? That's the special one, right? E to the x? According to the formula, it would be itself, e to the x, times natural log of what? That's right. That would be natural log of e. But natural log of e, we just said, was 1. And that means the derivative of e to the x would be itself. Exactly, itself. Exactly.
Like it's a constant. Not really.
Yeah, I understand what you're saying because it doesn't change, right? It just keeps, like, you could take the derivative 5 times and this would still be e to the x, right?
Not that big.
That is actually what makes e to the x so special, all right? You may have asked yourself, like at some point, and maybe not, like where did they come up with this e is 2.718, and why are they calling that the natural base, the natural exponential function, the natural log? Why is it that way? And it turns out that it actually worked the other way around. We didn't like find this number and then go, oh yeah, and then we'll just call a function e to the x. Instead, what we did is we said, is there a function that behaves a certain way? And we went looking for it and we found it, and that's the one that works. Let me try and explain with a picture. If I take the function x squared, let's do x cubed, all right? It looks like this, right? That's what x cubed looks like. If I go out to the x value of 2, where would I be on this curve? If I go out to 2, what's the y coordinate here? 8, thank you. 8, right? Because you plug 2 into this function, 2 cubed is 8, right? That's where I'd be?
We're tired too, don't worry.
You're tired? Is that what you're saying?
We're tired.
Okay. All right, y'all follow me though?
Yeah.
Now, if I asked you what the slope of the tangent line was there, what's the slope of the tangent line there? What would you do?
Find the derivative.
Find the derivative. What is the derivative of this? 3x squared. That would be your derivative. And what would you do to find the slope of the tangent line right here?
Put in the points.
Yes, what point am I going to put in there?
2 and 8.
Just, all I need is the x coordinate, right? So plug 2 in here, what would you get? 4, 3, 12, right? So if I draw the tangent line right here, right? If I drew it, whoa. the slope of that line would be 12, wouldn't it? Now, we didn't find the equation of the line, we just found what the slope is, yes? So what we did is we said, hey, I wonder if there is a function that when I go to some value, let's say I go to 2, and I go up to this point, and I plug it in, and I get some number out here, right? Let's just call this number y, okay? Y. I wonder if there's a function out there that when I find the slope of the tangent line, the slope of that tangent line is also how high you are off the ground, is also that y coordinate. Like, look at this one. The slope of this is 12, right? It's not 8. I wonder if there's a function where when you plug in 2, you get 8, but the slope is also 8. Then when you plug in 3, you get something, but the slope is also that. Got it? That's what the exponential function is. It is the function that when you go out to any point on it, the slope of the tangent line is the value of the y coordinate. So if I draw this, this is e to the x. I was kind of cheating here. So this is e to the x right here. Right? That's what it would look like. If I plug in 2, I'm going to get e squared, right? Which is something. Well, if I go and try and find the slope of the tangent line, the derivative of this, the derivative of that is itself, isn't it? Right here. So what's the slope of that tangent line? E squared. So the slope of this tangent line is e squared. Do y'all get that? This slope is equal to the height of the point. Everywhere on the curve, it's like that. Not just at one point, at every point it's like that. And this is the only function that does it. There's no other function that does it. It's unique. It's like, it almost like naturally occurs to be the only one. We'll call it the natural exponential function. Does that make sense? That's the idea. We went looking for it. This is the one that works. No other one works. Can't explain why it is that way, but it's the natural, we'll call it the natural exponential function. All right, now I want to adapt this formula slightly. Let's do it with this right here, e to the u. So this will be a formula that will incorporate the chain rule. What is the derivative of e to anything? It's e to that anything, right? It's itself. Then we'd have that natural log of e here, right? But that natural log of e is always going to be 1, so we are not going to write it. But then we have to account for the chain rule, so we'll tack onto this what? Times the derivative of u, or u prime. That is our more general formula. If that's the general formula, if that's the formula for just e to the x, that's it. But if we say that's something other than x, we would have to use the chain rule in here.
So say it was e to the 5th, for example.
E to the 5th?
Yeah.
Like y is equal to e to the 5th?
Yeah.
What's the derivative?
Yeah.
E to the 5th times natural log.
I guess it's a good thing I asked that.
Leah?
So it'd be 0. Yeah, because 5 is a constant.
It's 0. Yeah, you said e to the 5th, that's a constant. There's no variable in there, right? Now, if you want to change it to e to the 5x, I'm with you. All right, e to the 5x. Did I say that? Leah? Leah? Yeah. Okay, that's what I thought. Trying to learn names. I'm not going to learn them, but I try every once in a while.
We're just a number.
Yeah, thanks, man.
No, I mean, you're not, but I'm not good with names. I call you Bailey, but it's not Bailey. That's your last name, right? It's John? John.
My last name is Bailey. That's
Jay is your...
Everybody calls me.
Okay, so I call you Bailey. All right. All right. So change it a little bit. Put the x in there so that we can actually account. It's not a constant anymore. So derivative of e to something is going to be itself. E to the 5x times 5. You do not have to do the natural log thing on the e's. Okay, now if this was 4 to the 5x, then you would have to do 4 to the 5x natural log 4, then times 5. Yeah.
So rule of thumb, if it's e
E to whatever. Oh, e to a well, that is a constant, right? If you just get on a calculator and go e to the 5, that's a number. Derivative of a number is 0.
Be a fraction, whatever.
Yep, anything. Yep, e to the pi, it'd still be 0. Now, I want to do a little disclaimer here, just because what I've just told you. I said that this natural exponential function is the only one that behaves that way. There is another one that kind of behaves that way, and it's this function, y equals 0. What is the derivative of that? 0, right? And so it is its own derivative, right? But that function is what we call trivial. It's boring, right? What does that function look like if you graph it? It's just a flat line, right? It's just a flat line. It's not doing anything. So what we do to kind of throw a little more life into our exponential function is we say, find a function that is its own derivative all the time, but also at 0, if you plug 0 into the function, it's not equal to 0, it's equal to 1. So think about the function e to the x. If I say this is the function f of x, then what's f of 0? 1. See this one right here, if I plug in 0, what would I get? 0. If I plug in any number, it's 0, right? Very boring. So if we just add this one condition on here, find me a function that is its own derivative, but when you plug in 0, it's 1. The only function that will ever do that is the e to the x. All right, let's practice more derivatives.
So you're saying there that e to the power of 0 is 1. That's the only
E to the 0 is 1,
so that's
yes.
the only constant that it won't be 0.
That's the only function that is its own derivative, and it's not trivial. Like y equals 0, that function is trivial. It's doing nothing. You give it a value, it just keeps on spitting out 0. It's all it knows how to do. That's not a very useful function. All right, let's try this. How about x e to the x squared plus 1? Let's take the derivative of this. You got a product, right? Product rule. So we have the derivative of the first one, which would be 1. I'll put a 1. I don't need to, but I will. Times e to the x squared plus 1 plus the derivative of e to something, right, is itself, right? So I'm going to write e to the x squared plus 1 again. And then what after that? Times 2x. And that's it. Times x. That x comes from finishing off the product rule. So this e to the x squared plus 1 times 2x is just the derivative of this piece. And then you have to multiply times the x. I would factor out. I would factor out an e to the x squared plus 1. And be real careful, what would you be left with there?
1 plus 2x squared.
2x squared. That's it. So I pull this. This is a common factor in both of these terms, so I pull it out. When I pull it out of this one, I'm left with that 1. And when I pull it out of this one, I'm left with the 2x squared.
How is this used in everyday life?
How's what?
How is this used in everyday life?
Well, that's a very good question, and I'm not going to try and avoid your question, but I will say that you don't put people on the moon, you don't put satellites in orbit, you don't have modern day technology without exponential functions. It just doesn't happen. A lot of the framework that the world that we exist in is built upon the foundation of things that have been done already for us. And trust me, banking institutions use exponential functions all the time. That's how they compute your interest. How much money you owe. If you have a credit card.
I actually don't. So.
If you had a credit card, Okay, then if you have money in the bank, it's how much they're going to give you. It's based upon compounded interest. So exponential functions are used for that all the time.
Right, you're going to take my money.
But more importantly, it's used in solving what are called differential equations. Exponential functions. Now, we haven't studied differential equations in detail here, but I can give you a very simple example. That way you can kind of get the idea and then imagine that you could adapt it to something else. Let's say that you have an island, and on this island you have rabbits and you have foxes and you have vegetation and you have water, right? So let's talk about the populations on this island of rabbits and foxes. Okay, so the rabbits start growing, right? That population starts growing. That means the foxes, plural? Yeah, whatever. The foxes have food, right? So they start eating, and their population starts growing. And at some point, the population of foxes gets large enough that the rabbit population can't maintain itself because there's just too many predators. So the rabbit population starts to decrease. Less food, foxes start to decrease. And so what's happening in a situation like this is you have that the growth or decay of this population depends on not only how many foxes there are, but how fast these are growing or decaying. So every time, if you just look at how many are here, that's like a static snap picture in time. But every day, these populations are changing. So you're not only looking at the R, you're looking at its rate of change, which is a derivative. And then here you're looking at the number of foxes, but also it's their rate of change, which is a derivative. So this is called a differential equation. The relationship between those two populations involve the actual values of the variable, R and H, and the derivatives of each. So it is a differential equation. It involves derivatives of the variable. Different variables. And the exponential function, because it's its own derivative, allows us to attack problems like that a lot easier, because if it's its own derivative, it doesn't get more complicated. Does that make sense? So like you can, well, I mean, if I ask you to take 100 derivatives of e to the x right now, you'll laugh at me, right? Because you're just going to write e to the x. But if I ask you to do 100 derivatives of 4 to the x, now you're going to have to work at that. So e to the x is a very nice function. It's very useful when it comes to taking derivatives because it keeps things clean. It just behaves very well for us. All right. Oh, there was another one I wanted to give you here. How about this one? Y equals e to the root x. Let's take the derivative of that. So what is it? It's itself, right? E to the root x. Yep, times 1 over 2 root x. There it is. That's all. Does everybody have their exam? No? Hudson? Anyone else not have their exam? All right, that's it. You could maybe like write this if you wanted to. It wouldn't be any more correct, but you could write it that way, right? So in the homework, you're going to have an opportunity to practice with a lot more of this. We need to move on to the next topic, still within the same section, which is, well, if we know the derivative of exponential functions, logarithmic functions would come next, right? That would be what we need to know the derivative of now. So let me give you the formula. Actually, you know what? I can derive this formula easy. If you want, I can derive it. No? Yes or no? I don't care.
Just give it to us.
Just give it. I think I'll just give it to you this time, all right? y equals log base a of x. All right? Let me write it the way I've been writing. I'm just going to put that there and put it like this. Okay, that's the way I've been writing it. If I want to know the derivative of this, it's actually really crazy what this becomes. It's just 1 over x natural log a and that's it. So let me show you an example. What is the derivative of log base 7 of x? I always imagine that the derivative of a log, all it does is it just like spits out what you're giving it down into a denominator. Right? So like x was in here, just spit it out into a denominator. 1 over x and then times natural log of 7. That's all. Remember, natural log of 7 is a number, right? Now, you didn't want me to prove it, so I'm just, that's what it is. How about this one? What's the derivative of log x?
That's understood as log base 10.
That's right, good. That is understood to be log base 10. If it's not written, if a number is not written down there, it's understood to be log base 10. And so we write 1 over x natural log 10. That all right? Then what's derivative of natural log of x? All right, see, that's why I don't like this notation. It freaks everyone out. You just told me right now that this was log base 10 because it was understood, right? That's the same thing. That's understood to be what? Log base e. Log base e. That's why I hate that notation so much. Is because students lose complete sight of the fact that that is just this with an e. So this is the derivative of this is going to be 1 over x natural log of e. But natural log of e is 1, so it's just 1 over x. Ooh, that's really nice. Let me recap that. The derivative of natural log of x is just 1 over x. Just like the derivative of e to the x was real clean, it was e to the x. The derivative of natural log of x is really clean. It's just 1 over x. So you take derivative of natural log, all it does is does 1 over whatever was inside of it, goes on the bottom. Now let me see if I can stretch this. Can you tell me what the derivative of natural log of u would be then? It's still log base e. So you're still going to get that 1 down there, right?
Just 1 over u.
It's 1 over u, good. But there's one more thing we have to take into account.
The derivative of
The derivative of u, right? Because this is more like chain rule. What's the derivative of what's in here has to come out here, doesn't it? Times u prime. And sometimes you'll see people just write it like that. U prime over u. So the derivative of natural log of something, doesn't matter what it is the derivative of that something over itself. The derivative of that something over itself. This is a big formula right here. That only works for natural log though, right? If it was log base a, then your formula, you'd have to include that natural log of the base in here. So let's try a couple of examples. Oh, you know, I never turned the lights back on. That's why it seems so gloomy in here. You like it? I'll just leave it? Okay. All right, so as an example, if y equals natural log of 3x squared minus 4x, what is the derivative of this? That is going to be chain rule, right? It looks like this one, right?
Yeah, so then 1
I could do 1 over
whatever's inside.
times the derivative of what's inside. Okay, I'll write that way. Y prime would be 1 over 3x squared minus 4x times u prime, which is the derivative of what's in here, which is 6x minus 4. Do I need that in parentheses? Yes, absolutely. Now we could slide that on top and write 6x minus 4 over 3x squared minus 4x.
So by doing that, we can got rid of the log.
Yeah. The derivative of the log of something is the derivative of this something over itself. U prime over u. That's a cool one. If you like that one, you'll like this one too.
It's another formula.
Nope, just an example. All right, I'll put it. The derivative of the natural log of cosine x. What's the derivative? So 1 over cosine, I didn't hear that. Is that what you said? Okay, 1 over cosine x times negative sine x, right? That's what we have. And then you can say that's negative sine x over cosine x, which is negative tangent x. Now be careful with what we just did. What is the derivative of tangent x? Secant squared x, right? This is the derivative of, where is it? Natural log of cosine x. So thinking now, again, let's go back to like Cal 2, because that's where you're headed. If you have to do the antiderivative of this, see, it's going to be this. Do you see? That's a little harder to go backwards from that to that, right? It would be very easy, right? Yeah. Oh, yes, exactly, right? Going forward is differentiation. Going backwards, a lot harder. All right, so look, how could I make this? I really wish I could have got a tangent, not a negative tangent. So how could I have changed the original problem so that I get an answer of tangent instead of negative tangent?
Negative cosine.
Just, why don't I do y is equal to negative natural log of cosine x? Wouldn't that negative, I have to write the negative, sorry. Y equals negative. If I do that instead of this, that negative will follow me down the whole way, and then it'll hit that negative at the end and it'll become positive tangent, wouldn't it?
So the antiderivative is like the... Never mind.
Yeah, don't worry about it. Okay, so we could work this through, right? The derivative of this should be tangent, shouldn't it? Okay, I'm going to write something. I'm not taking derivative. I'm just going to write something. Do you agree with this? Is negative natural log of cosine x equal to natural log of secant x? And if so, why? Okay, it is. I'm telling you it is. Now why? I'll start to give you hints here. This is -1 times natural log, right? Okay, I hear you're on the right track. Hold on.
It's like a product rule.
I'm not doing a derivative.
Okay.
This is no derivatives. I'm just rewriting it. Where were those properties? Where was that one I starred earlier that I said was real important? This one right here? Remember that? It said if you had a log and you had a